Hello, welcome to this video on trees, binary trees, and binary search trees. My name is Nzako Baloyi, and I'm pleased to take you through the material. By the end of the lecture, we hope to have achieved the following: to have established a basic understanding of the tree data structure, an appreciation of the terminology that surrounds the tree data structure, binary trees, and binary search trees. Just note that we will, for the purpose of this video, not focus on the practical elements of trees. And by way of introduction, a tree data structure is considered to be a collection of nodes linked together by edges to simulate a hierarchy. Now, the edges that we talk about here are unidirectional. That is to say, they prevent any cyclic behavior in a tree. The tree data structure basically simulates a natural tree, but in an upside down position. The reason for that is the root node of a tree data structure is at the top instead of at the bottom, similar to natural trees. A tree data structure can have as many children or child nodes as possible. At the very top of the tree data structure is what we call the root node. That node has no parent. You'll notice as we proceed with this lecture that with trees, we basically use terminology that relates to what one could call a family tree, as one would in such a case have ancestors, parents, siblings, etc., as well as terminology relating to the natural tree, such as the root node that I've just spoken about, as well as leaves. Now, on a tree data structure, a parent node is basically a node which is an immediate predecessor of another node, or a node directly above another. By that is meant that the parent node is a node that has at least one child. A child node, on the other hand, is a node directly below another node, or an immediate successor of a node. Put differently, a child node is a node that has a parent. We also have got siblings in a tree, and siblings are basically children of the same parent node. At the very end of the tree, the last layer of a tree consists of what we call leaf nodes. A leaf node is basically a node that has no children, in contrast to a root node, which is one that has no parent. An ancestor in a tree data structure is any predecessor node on a path from the root node to the node one is concerned with. By way of example, if you want to consider myself as a node in a tree, anyone within my genealogy that is older than myself, so my parents, my grandparents, my great-grandparents, and so forth, become my ancestors. In the same way, in a tree data structure, any node on a path from a particular node until one gets to the root is basically an ancestor of a particular node. That means even one's parent is an ancestor. A descendant, on the other hand, is a successor of a node on a path from the node itself until you get to a leaf. If you consider myself by way of example again, any child or anyone that is within my lineage until you reach where the generation ends, it could be a grandchild or so forth. But to qualify that, there has to be a linking path from the current node until the leaf node. Alright? Further concepts around trees, which now address other aspects of the tree, are, for instance, what we consider a path, which is basically a sequence of consecutive edges or consecutive nodes from the source node to the destination node. It is important that these nodes must be in sequence because they speak of a particular path or direct one towards a particular destination. Just as a way of example, if one were to consider a path from Pretoria to Johannesburg, it would not make sense to list the nodes in such a way that one mentions Midrand before they mention Centurion, because one would come through Centurion to get to Midrand on their way to Johannesburg. So it is important that the sequence be consecutive of the nodes or edges from the source node to the destination. Edges are basically unidirectional links between nodes. This is so as to maintain the property that a tree cannot be cyclic. A subtree, on the other hand, is a node with its descendants. So in a big tree, you find subtrees. A quick example will be if in a tree you've got, as part of the tree, a parent node that has got children. That parent node and its children are also a subtree of the broader tree, but we'll see an example of this in the next slide. The degree of a tree is basically the maximum number of children a node can have in a tree. Think of it this way. When you consider a binary search tree, its main property is that it must have at most 2 children. That means the degree of a binary search tree, of a binary tree rather, is 2. So, since I said earlier that a tree can have as many children as possible, if for a given tree you have a node which has the highest number of children being, for argument's sake, 10, and the rest having lesser children, the degree of that particular tree will be 10. Depth, on the other hand, is the length of a path from the root node to a particular node. Put differently, it is the number of edges from the root node to a particular node. That is what we call the depth. The height, on the other hand, is the number of edges on the longest path, underlined longest path, from the node to a leaf node. Put differently, it is the length of the longest path from a particular node to its descendants. It is essential that we consider the longest path because if you consider a given node, root node, with a short left subtree and a big right subtree, it is clear that the left subtree cannot determine the height of that particular tree because it's shorter. The height of the true height of the tree will actually be determined by the longest path, which is most likely going to be on the right side, in the example that I've just given. A level of a tree is basically the number of edges from the root to a particular node. You'll notice as we proceed that the root node is considered level 1, the next level is, rather the root node is considered level 0, the next level is level 1, level 2, like that, almost like an index in an array. Now, there are certain properties that you can come up with from these definitions, one of which is to say the level of a tree is the same as the depth of the tree. So when you compute the level of a tree and you compute the depth of a tree, you come to the same conclusion. Likewise, the level of a tree and the length of a tree are the same thing. Okay? On the other hand, the level of a node is not the same as the depth of a tree. The reason for that is, if the node you are starting from is not the root node, it therefore cannot be equal to the depth of the tree. It is only if the node that you are starting from is the root node that it will actually be equal to the depth of the tree. Moving forward, this slide gives you basically a summary of some of the concepts that I've just presented. To the far right, you'll notice that where the root node is level 0. The next level is 1, 2, and 3. Secondly, the topmost node is called the root node. The B and C in this given case are the children of A. But if you consider A, everything on its left can be considered its left subtree, and everything on its right can be considered its right subtree. In the same way, this F, I, and J can be considered a subtree, the same way that C, F, I, J, and G can be considered a subtree. Okay, now B in this particular case is actually a parent to D and E, and it's likewise a descendant of A, but an ancestor of D, E, and H. H is also a leaf node because it's got no children. The same you can say about I, J, and G. Moving forward, perhaps before I move forward, there's a concept I omitted to mention here. When you look at a path, let's say for argument's sake you want to get to H. A, B, D, H is the path from A to H. In the same way, A, C, F, J is the path from A to J. Another thing, if you want to consider the height of this particular tree, you want to look at the longest path. That longest path, you will notice, will be about 3, because this level is the lowest level, or the highest level rather, and therefore that is what would enable one to get to a more reflective height of the tree. So you could say if this is 0, this is level 0, then it is at level 3. So you could even count it as 1, 2, 3, 4, for instance, or as 0, 1, 2, 3, which allows you then to understand the height of a particular tree. So the height of this particular tree is found at level 3. But when you count it as height, using the height, you'll have to count 1, 2, 3, 4, meaning the height of this tree is 4. Talking about binary trees, I've spoken about this a bit earlier. A binary tree is basically a tree which has at most 2 children. In other words, it can have 0, 1, or 2 children. Others define it as a connected, unidirectional, finite graph with no circles. It has no circles because it's undirected, remember. On the other hand, there are various operations that can be performed on a binary tree. Some include the depth, which we have spoken about, the size, the height, the search, or the transversal, the removal, as well as the insertion of elements. Another concept that relates closely and even progressively from discussing trees to binary trees is what we call the binary search tree. Now, the binary search tree has a specific ordering so as to facilitate quick searches. So its main purpose is to make search operations more effective and efficient. Now, what are these ordering properties? The ordering properties of the BST or the binary search tree are that the left node of a particular root or parent node must be less than that particular node, whereas the right node must be greater than its root or parent node. I'll repeat that again. Given a node, its left child must be less than the node itself, and its right child must be greater than the node itself. Simply put, when you think about insertion or addition, for each element that you want to add, it's important that you first check whether it's bigger or smaller so that you can know which side it belongs to, whether the left or the right, because of that ordering property. In other words, you can't haphazardly insert elements. You need to know whether they belong to the left subtree or the right subtree. In other words, is the element less or greater than the parent or the root? You then have to repeat the same test until you get to where the node belongs. Another operation one can perform is a removal, which is when you remove a particular element or node from the tree. Another is a find or search or traverse, which is used to locate, or traverse rather, used to locate a particular element in a node, a particular element rather in a tree. Each search iteration rather, in a binary search tree eliminates at least half of the remaining elements from the search. So if you think about it, if you started off with a tree with 100 nodes, and after the first iteration or the first check, because through that check you determine whether you go to the left or the right of the node, and if that allows to eliminate at least half of the other side of the tree, because if you go left, it means you will never treat the right side of that tree, which is great because you don't have to worry about it. That is what makes the BST very efficient. Now, something can militate against that efficiency, and it's called an unbalanced BST. Where does one get to such a situation? Where you find yourself, for instance, with ordered elements in ascending order, you'll end up with a balanced tree similar to one that you have at the bottom left, where you have a right skewed tree. Whereas if the elements are in descending order, you'll have a left skewed tree. The problem with this is that its complexity is that of order n, because for argument's sake, to get to G, you have to go through every other element. Now, a balanced tree, on the other hand, is exemplified on the picture to the bottom right of the corner. And that you can see just by looking at the tree that it is well structured. That if you are looking for C, for argument's sake, when you start at D and realize that C is less than D, you have already in that first step eliminated the right side. You get to B, you check is C greater or less than B, you find that it's greater than B, you have effectively eliminated the left side of B. So with every iteration, you are eliminating a huge chunk or about half of the elements to allow you to proceed further, which reduces your processing time and the number of steps you have to go through to get to a particular solution. Now, let's look at an example of a binary search tree, but this is an insertion example. For starters, we insert 5, which becomes our root node. You'll notice that we're pointing to the root node because that's the only pointer one needs to keep to the root. The next thing we do is we insert 9. Now, you have to compare 9 to 5 before inserting it. Does it belong to the left or the right? The decision is based on whether it's less or greater than 5. But we know that 9 is greater than 5 and therefore it will belong to the right. Next, we have to insert 7. To insert 7, we first check with 5. It is greater than 5, therefore it belongs to the right. But it's less than 9, therefore it belongs to the left of 9, which is why it came right here to the left of 9. We now want to insert 3. 3 is less than 5 and there's nothing on the left child of 5, therefore it sits directly as the child of 5 on the left. We then want to insert 8. 8 is greater than 5. It's less than 9, but it's greater than 7 because there's already an element there. It's greater than 7, therefore it sits right there. So you'll notice that you check at every level where a particular element will fit. Now, inserting 12 is greater than 5 is greater than 9. It sits there because there was nothing as the right child of 9. We insert 6. To insert 6, 6 is greater than 5. It's less than 9. It's less than 7. And therefore it sits there. To insert 4, it's less than 5. But it's greater than 3, which is why it will sit there. To insert 20, on the other hand, is greater than 5, greater than 9, greater than 12, and therefore it will sit as a right child of 12. I hope you're following thus far. Next, we'll look at a deletion. Now, we start by, this is the initial tree that we have, and we want to delete J. Look at where J is sitting. It's sitting as a leaf. To delete J is simple. We just remove it, and you see, it's no longer there as a child of H. The next stage is to delete C. Where is C sitting? It's sitting as a child of D. After this deletion, I need to explain something here. Whenever you delete a node that has children, you have two options. You replace that node with the highest or biggest child of the left subtree, or the smallest child of the right subtree. Okay? It's either you replace with the biggest on the left or the smallest on the right. Simple. Now, but C here has only one child, which is A, so A will automatically take over the position of C, which is why after deleting C here, we point directly from D to A. Now, to delete L, the principle that I've just explained applies. You either have to replace L by the highest child of the left subtree, which will be H, or the smallest child of the right subtree, because there's only P, it would then be P. Okay? So in this particular case, when we delete L, we decided to use this left subtree, and therefore H went up. Now, but with H going up, because H itself moving up, it's almost like a deletion. Where does F then go? It takes the position of H. Why? Because it is the highest child of the left subtree of H, and therefore it moves right there. Okay, which is the tree that you see there. To delete D, on the other hand, you see where D is sitting, you apply the same rule. So in this particular case, we only have got two children, left and right, therefore any of them can really replace it. In this case, we decided to replace it with A, which is why you see this particular subtree here. Lastly, we want to delete A. To delete A will just be replaced by F, which is that subtree right over there. Okay. It is important to also understand that there are different types of transversals. There's in-order transversals, pre-order transversals, and post-order transversals. Let us now start by having a look at in-order transversals. Within order transversal, you start with the left child, you go to the root, and then you go to the right. If you think of basic operations that we perform on a day-to-day basis, think of A times 2. You start with A as the left, the multiplication side as the root, and the 2 as the right. So it is something similar that you'll notice here. This in-order transversal is the most commonly used because it simulates or emulates what we are used to. Okay, let's look at the tree at the bottom right. With this tree, which is basically using in-order transversal, we start with the left. So we say the left, which is 3, its root or parent, and then its right child. So it's left, root, right. So it's 3 plus I. Okay? But by doing that, it means we have just addressed this left aspect. And because we've addressed the left aspect, we now are entitled to deal with the root. And therefore, after 1, not I, sorry, we can then say multiply by. And then the right child, which is 3. But we've also again dealt with this left aspect. Therefore, we can go to the root, which is divide by. Now, from divide by, it's important to note that we cannot from divide by go straight to plus. Why? Because we have to start by dealing with the left. Remember that plus is a root of something else or a parent of something else. In the same way, that minus is a root or parent of something else. Therefore, we must start with the left child and then treat the root, and then we treat the right child. That allows us to have computed this part, and then we'll go to that root, and then we'll go to its child. Then, by doing that too, we have effectively exhausted the left side or left subtree of the root node. And therefore, we are now entitled to now invoke the root, which is minus. And then we'll go to the left again of the right side of the subtree, which is then 3 times 7. Remember, we can't go directly to minus because minus as a child. We start with the minus, the left child of minus before we call minus, which is root, and then we go to its right. The same way we then go to that side because we've just dealt with this whole subtree. We can now go to that root, and then we'll go to 6 as the right child. And that is basically it, as simple as that. So those arrows will help you understand basically where we go at which stage. Now, talking pre-order transversals, they start from root, we then go to left, and then we go to right. Unlike the in order, which was left, root, right. Here was starting with the root, and then we go to the left and then the right. Example, we start with paper because it's the root. Then we say title, abstract, and then from here, we don't come to 1.1 because we start with the root, remember? So we'll start with its root, and then go to the left child, the right child. To the next one, we start with the root, the left child, the middle child, and then the right child. And in this particular tree, you'll notice that actually the degree of this particular tree will be 6. Please take some time to check why I said the degree of this particular full tree is 6. Anyways, I was still here. We say 2.1, 2.2, and 2.3, and then we'll go to that little root, go 3.1, 3.2, and then we'll go to the last child of paper. And that's it. It's as simple as that. Next, what we now need to do is we need to look at post-order transversal. Now, how does that work? We start with left, we then do right, and the root at the end. It's almost the opposite of pre-order. Now, we therefore start with title, abstract, okay? And then we go 1.1 because we start with left, and then we go to the right, and then we go to the root. This particular root we can treat because we've exhausted these children. And then we go to the left, the middle, the right, and the root because we've exhausted everything else. The left, the right is a root, and then the last child of paper. Once you deal with the last child of the root, which is paper, then you can go directly back to paper. That was how we dealt with left, right, and root. That's post order. Okay, as a high level overview, this just gives you a summary of how you would represent the given tree using in order, pre-order, and post order. Remember, pre-order, you start with the left, root, right. In this case, it will be B. B on the left, F as the root, G, H, okay, and then we'll go to P. Then we come to R, all right, because it's the left child, and then you go to, after R, you go to S, the root. But as soon as you do S, on the right side, you have T. Now, if T had a child, we'll start with its child before we consider it. But because it doesn't have a child, we'll say root, and then right child, and root, and then right child, which is Z. And then we're done. Okay? Let's go to pre-order. Remember pre-order? Okay. Pre-order is root, left, and then right. So we say P, then we go to the left, which is F, left again, B, okay, and then to the right, we go to H, and then we get G. From there, we go to root, that side, which is S, to its left child, R, and then we go to Y, its right child. And then from there, we go to T, and then from T, we treat its right child, and then we go to the right child of Y, which is Z, and we are done. Post order, on the other hand, we have to start at the left, right, and then finish at the root. What does that mean? It means it will then be B. But instead of immediately doing H, we'll have to do G, because by doing H, H is already a root of something, which is G. So we have to do its child first. So say left, H is left child, and then we can do H. So it's B, G, H. Okay? From there, we can exhaust this by going to F. Then we've exhausted the left subtree. From there, we have to go to the left of this other subtree, which is R. From R, because it has to be left, right, root, we cannot take S as yet. Now, we have to go to the right. But before we do the right, we cannot just say R and then W because it's got children. You can't start with a root when you have a child. Okay, so from R, you have to go to W, and then you can do that root. And then you have to do this Z, and then you can do that root. And then you can do that root, and you do that root, and you are done. As simple as that. Okay? Now, there are formulas one could rely on to determine the children of a node for elements stored in an array. For the left child, one can use 2 times index plus 1. Let's just take this example. And for the right child, one can use 2 times index plus 2. Let's take H here, which is at 5, right? If you multiply 2, right, by 5, or rather, let's take something else, because we want to determine the child. Node. Let's take 3 rather, so that we can find something that already has a child. Because we know that B has children, right? So let's take B. We say B, which is 3 times 2, it gives us 6, plus 1 gives us 7, which is A, and plus 2 would have given us 8, which is C. Are the children of B, A, and C correct? The B is A and C. Now, to determine the parent, we also have a formula for that. Let's check here. Let's take H for argument's sake, which is at index 5. We subtract 1, it will give us 4. We divide that by 2, it will give us 2, which is here. The question is I the parent of H? Let's check. I indeed is the parent of H. You can use also the second formula and you'll see that it also works. So we're good on that. Moving on. Okay, let's look at complexity now. It's important to notice that a binary search tree has order of log n complexity for find, insert, as well as delete. And you can see it clearly on this table for retrieve item, for insert item, and for delete item, which is what we're looking for. Okay, so it is quite an improvement because now we can perform these operations not with order of n, but with order of log n, which is much, much smaller in comparison. Okay, this then makes binary search trees very useful. Okay, as a conclusion, we introduced trees as a collection of nodes linked together by edges. I introduced you to the terminology that surrounds trees. We also learned that binary trees are basically trees which have at most 2 children. Binary search trees, on the other hand, we learned that it is a tree where, given a node, its left child is less than that node, and its right child is greater than that particular node. We then looked at different types of transversals, which is in order, post-order, and pre-order. And we looked at a few examples of insert and deletion, as well as the complexity of operations. With that, I want to say thank you, but before I go, there's an exercise I'd like you to now pause this video and do. And after doing the exercise, you will find the solution in the next page. That is the solution. If you have difficulties with this, please do not hesitate to drop me an email and I'll be glad to assist you. With that, please have a look at the references. Use the video links as well as the study material to bolster your knowledge on trees, binary search trees, and binary trees. And I thank you. Till we meet again.